welcome all the participants and our very distinguished speaker, Father Richard D'Souza from Rome, Vatican Observatory, Director of Vatican Observatory. And today we have host Dr. Reshma Raut Desai. He is Assistant Professor in Physics Department of Goa University. And I will request now Madam Reshma to take over and start the session, please.
Yeah.
Dr.
Good evening. Yeah. Good evening, everyone. Good evening, Father. First of all, I'm very happy to see you because I had a chance to host you at St. Xavier College when I was teaching there, but it did not happen. And now I have joined Goa University. Yeah, it's me. Okay, so on at least online, I have an opportunity to hear you through NASNI. Let me welcome once again everyone for this very special talk of NASNI today, and also to our resource person, Reverend Father Richard D'Souza. Before I invite Father to start today's session, here let me give you a very brief introduction of our guest speaker today. Our guest speaker today, Reverend Dr. Father Richard Anthony D'Souza, is an Indian Jesuit priest and professional astronomer, and who is currently serving as the director of Vatican Observatory, which is at Rome, Italy, which is one of the oldest astronomical research institution in the world. He has earned his PhD in astronomy from Ludwig Maximilian University, Munich. His research was focused on stellar halos of galaxies, and has held a postdoctoral fellowship at the University of Michigan, Ann Arbor. Trained in physics, philosophy, and theology, he uniquely integrates scientific research with education, leadership, and public outreach. He is a recipient of Kippenheim Prize and actively contributes to the global astrophysics community through research, teaching, and scholarly service. Today, he's amongst us to deliver a talk on the topic, the Vatican Observatory efforts to understand the effect of mergers on Milky Way galaxy. On behalf of all the members of NASNI, so I welcome you and I request you to start today's session.
Thank you. Thank you, everybody, for this warm welcome, and thank you, Professor Reshma, for welcoming me. It's a pleasure to talk to all of you. Today's talk, I will give you a mixture of both a little bit I will talk about the Vatican Observatory, what is it? And then I will move into science, because that is my passion, to talk about science and some of the amazing discoveries we are doing today. So let's start off just a small move in history. The church's contributions to astronomy. It is often said that the church has opposed astronomy, but if one really does read history, one finds that right from the 16th century, the church got very much interested formally in the acts of astronomy, studying the stars. And the main reason it was interested in this is because of what is called as the reform of the calendar. The calendar we use today is called as the Gregorian calendar. But before this, in the 15th century, we were using the Julian calendar. And the Julian calendar had some certain problems. And more than that, the problems were basically that they calculated the day of, they calculated that the earth goes around the sun, or the sun goes around the earth, to be exactly 365 and a quarter day. And with this assumption, as we know, it doesn't exactly do this. It's slightly less than 365 and a quarter. And over time, this adds up. And so the seasons and the months slowly got out of sync. And the church wanted to rectify this for many purposes, and so started to actively study astronomy. And the first person to do this, among the first people to do this, was a certain priest, Father Christopher Clavius. He's a German priest. And with him, they started the reform of the calendar, which we use till today. Basically, he calculated the Christian feast days. So, how do you calculate Easter, and the other feast days? And so he calculated these feast days for the next 5,000 years. It was an amazing feat of calculation on his part. We also have, it's a nice example of how well they were. The first map of the moon was also made by a priest, Francesco Rimaldi. And you will see that many of the craters of the moon, which he puts there, which he drew by hand, he named after his friends or scientists of the period. And therefore, there are many craters of the moon named after Jesuit priests or priests in general. About 35 or 36 of them are named after Jesuit priests. The other great astronomer priest in that period, supported by the Vatican, was Father Angelo Secchi. He is considered as the father of astrophysics. And he was the first person to systematically, so you all know what Kirchhoff and Fraunhofer did, the Fraunhofer lines, where they put the light of the sun through a prism and studied these absorption lines. But Father Secchi was famous in doing this for thousands and thousands of stars, of distant stars. So the distant starlight put through a prism and then study the lines of the stars and be able to then begin to have the first classification of stars. So he is considered today as the father of astrophysics, because he not only began studying how the stars were moving, but he was more interested in what the stars are made up of. And he really believed, after the discoveries of Fraunhofer and Kirchhoff, that you could, through these lines, really get to what was present in the stars, the composition of the stars. We have the famous Cartousiel project. This was a French project to make the first detailed map of the sky, and the Vatican took part in this. This is a predecessor of the maps of the sky that we use today, which you use in your applications, in your phones or in any other of your devices. And Gaia, the project Gaia, or the European satellite Gaia, is a successor of this great project, the Cartousiel. And this was taking place within the Vatican. Perhaps the most famous of the church's men in astronomy is Father George Lemaitre. And George Lemaitre is famous because he worked with Einstein, the equations of Einstein, on general relativity, and was the first to apply general relativity to one of the first, not the first, to apply it to the cosmos. And he realized that you needed an expanding universe. And we have the famous Hubble law, which has now been named as the Hubble-Lemaitre law, because they more or less proposed it at the same time. But Father George Lemaitre went even further. He proposed that the beginning of the universe, what we commonly call as the Big Bang theory, comes from Father George Lemaitre. So the proposal of the Big Bang theory actually comes from a Catholic priest. So So these are a few examples of the church's involvement in astronomy over the years. So today, this is embodied in this Vatican Observatory, which is sponsored by the Vatican. It goes, although it was refounded in 1891, its story goes back to the 16th century. It is a small observatory. We are not many people. We are 15 just in this observatory, and we are divided in two locations. In Castel Gandolfo, outside Rome, Italy, and we have a 2-meter telescope on Mount Graham in Tucson, Arizona. And that's where we do our main observing in the US today in Tucson, Arizona. So this is a bit about the Vatican Observatory and the story of how the church has been involved. Why do we do astronomy? First of all, all of us love astronomy. So that's the main reason why we do astronomy. But on the part of, on the church and the Vatican, they want to show everyone that faith, anyone's faith and the science should be able to go together. There shouldn't be a division between faith and science. So both of them should go together. And this is the main reason why the Vatican Observatory continues to exist, to show how faith and science goes together. Okay, let's move ahead. I just want to show you that these are the asteroids named after Jesuits who worked at the observatory. So there are a number of them there. This is a bit of an older plot from February 1, 2023. Every year we add 4 or 5 new asteroids, which are named after Jesuit priests. But I want to talk to you about something really different today. And I will move to the next topic. And I want to talk to you about mergers of galaxies. This is my passion. So I have before you an image of the Milky Way as we see it from Earth. It is a wide image on a dark night, you will see. And we know that the Milky Way has about 1 billion stars, right? It has about 1 billion stars. It is one of the most common galaxies found in the universe. Okay. And just you are all astronomers, so you have a sense of the dimensions of the Milky Way, and we know that our sun is about 8 kiloparsecs away from the center of the Milky Way. So we are about halfway distant between the center of the galaxy and its outermost radius. We can define about to be 15 kiloparsecs. Okay. So let's move ahead. So the closest galaxy of the same size as the Milky Way is the Andromeda galaxy, the most famous nearby galaxy. And that is about, 780 kiloparsecs, about 0.8 megaparsecs, okay? And so if you look at the universe around us and you throw galaxies into this universe and you see the distribution of galaxies, and if you were to ask the question, hey, what is the typical distance between 2 galaxies, which is the size of the Milky Way, about our size, you can say that it is about 1 megaparsec, 0.8 megaparsec, about 0.8 to 1 megaparsec. And that is the typical distances. They're quite far away, these guys. So this is the closest Milky Way mass galaxy, and there are millions and thousands and millions of galaxies much further away, like the Milky Way. But all of them are about a distance of 1 megaparsec from each other on average. Okay. So you have millions and millions of these galaxies in the universe. We all know this. This is an older image from the Hubble Deep Field taken by the Hubble telescope. It was many hours went into this image. And here comes the question, right? So we have various types of galaxies uh, in the universe. So in this column, in the middle column, where you have these three galaxies, one on top of each other, that is about the size of the Milky Way. And you can see that in each of these columns, the size increases by a factor of 100. So there is a great variety of sizes of galaxies in the universe. And there is also a great variety at the Milky Way mass of different types and shapes of galaxies. So one of the big questions in galaxy formation and evolution is to understand how do we get here? How do we get this vast distribution of galaxies? Why do galaxies come in different shapes? Why is the galaxy on top like a thin disk and one below it looks like a thin disk, but there is this oval lenticular shape of the galaxy? Or why is the galaxy, which is the most massive one, the M87, why is it round? These are the questions we would like to ask, okay? So the basic question is very simple. How do galaxies grow? So the galaxies can grow in two ways. They can do the hard work themselves. They can form stars. So we know how stars are formed. There is a cloud and dust of gas, and this gas compresses under gravity. And when it becomes extremely compressed and dense, then the temperature rises and it ignites. So what you see on your left, these nebulae, the Eagle Nebulae in our Milky Way mass galaxy, those are seeds of star formation, stars being born in our galaxy. And so you can grow the galaxy, make it bigger by growing stars, new stars. So that's one way of doing it. But you can also do a different way of growing galaxies. And this is by merging galaxies. That means let's take one galaxy and you merge it with a similar size, it grows double, right? So it becomes double the size and very fast. And why do galaxies merge? Galaxies merge because of gravity, okay? So think of it even in companies, you have companies in businesses. Businesses can grow by doing the hard work themselves, or they can acquire other companies. They constantly buy other companies. So this is what we call as mergers in businesses. So similarly, galaxies can grow in these two ways. Now, one of the questions which is really important in astronomy is this diversity in the shape of the galaxies at Milky Way mass, is it caused by some process inside the galaxy? That is, as stars are growing, something inside the galaxy makes it deform its shape? Or is it caused by merging two galaxies, right? Is it caused by merging two galaxies? So we see galaxy mergers like this. This is a very classic example of M51A and M51B merging. We see them merging before our very eyes. This is also a Milky Way mass galaxy. And the question is, what would be the final product of the big galaxy when the smaller one completely merges in it? Yeah. So this is the question we are trying to pose. Okay. So we see lots and lots of examples of mergers in the universe. Lots and lots of examples of mergers. This is like a snapshot of pictures of mergers from the Hubble Space Telescope. Yeah. So the question really is how do we understand what does merging do? Now, in an image like this, you can see things are merging, but you do not know what is the end product. You do not know what is the end product because you would have to wait billions and billions of years for find the end product. And so the question really comes is, can we take a galaxy like this one, for example? This is the lenticular galaxy, the Sombero galaxy. And can we, by some magical means, infer what are its past history? So this, what I'm showing you on the right, is like a small cartoon of the mergers of galaxies. So you have the galaxies on top merging, and they form the ones down, and these merge with other galaxies. And finally, you will have mergers of galaxies. So the end product is made up of all these galaxies before it. So what you see is the end product. But can you infer its past? It's a bit like being an Indiana Jones, a galactic archaeologist. Okay, Indiana Jones, a galactic archaeologist. What does an archaeologist do? He goes to an archaeological site and he tries to infer the past. What was this site about? Who were living here? What was people doing at that time, etc., etc. So this is important. How do we merge? How do we find the history of these galaxies? So now what I'm showing you in front of you is a simulation. It's a simulation of the mergers of galaxies. And what you see is as the galaxy grows, things keep on falling within the galaxy. Smaller galaxies keep on merging. And of course, the thing in the center keeps growing, but you see all these things around it. The thing in less white is like as the galaxy falls in, it gets ripped apart. So look at this galaxy falling, it gets ripped apart, and its stars are thrown all over the place. Thrown over the place. Of course, the biggest one falls in the center, but there are stars being thrown all over the place. So this is an example of a computer simulation example of a merger of galaxies. And the question is, if we look at the final product, now this is the final product at the present time, can we infer what fell in? Okay. This is the classic question which we are posing today. Okay. So that was a simulation. This is a real example of a galaxy, and you can see the shells around the galaxy. And these shells, now this image may mislead you. This image is a very deep image. So there is a big contrast between the shells of the galaxy and the central surface brightness. And if you have this magical ability to look very, very faint, you will be able to see all these shells around galaxies. And this outer part of the galaxy is called the stellar halo. And that is what we study in my field. We study the outer part of the galaxy, what we call as the low surface brightness region of the galaxy. So let's say our galaxy, as I was saying, extends to about 15 kiloparsecs, from the center to the outskirts. we are talking about anything from about 40 to about 70 kiloparsecs in radius from the center of the Milky Way. So, what are the stars in the outskirts from 30 kiloparsecs outwards? What are all these stars at the center on the outskirts of the galaxy? Okay. Now, these are again images of the outskirts of galaxies. And you can see the central image is the normal galaxy you see. But if you have a magic ability through special telescopes to look very, very faint, much fainter than the night surface brightness, you go to a very dark spot or you take a very long integration time. That means you observe for very, very long. You will be able to begin to see all these outer parts of the galaxy. Okay. Now, this outer part of the galaxy is the stellar halo. Okay. And in part, I like to now to bring your imagination, I like to start with another analogy, which maybe will be easier for you to understand in terms of galaxies, right? So think of, let's move away. I spoke to you about business. I will give you all an example now of a young family. So think of a young married couple, a husband and a wife who have a small child, like one that's about a 1 year old child. But now both the mother and the father need to work, and so they take turns in taking care of the child and feeding the child. So one day the mother comes back home from work, and it is the turn of the father to feed the child. And for a brief moment, the father leaves the child alone, in a chair, which is a special chair for children. So he's safe. The child cannot speak much, blah, blah, blah. He says, Mama, Papa. But the father goes down for a minute to throw the garbage out. So he's not there. And the mother comes back tired. It's time for dinner. But she's wondering now, has my husband fed my child? And how do I know this? Now, she is a very smart wife. She knows her husband very well. So what she does, she immediately looks on the floor around the child. And knowing that her husband never cleans up, she realizes that she sees on the floor grains of rice, grains of bhaji, a little bit of dal. As the child is eating, something goes into the mouth, but a lot of it also falls out and falls down on the floor. And immediately, this very smart woman begins to try and infer the past. Oh, my husband today fed the child, and he fed the child a bit of rice, a bit of bhaji, a bit of dal, and she tries to get to the history of what the child was fed. And so the question which we are looking is, he looks at the breadcrumbs around, the breadcrumbs. And so this stellar halo, which is made up of stars, are like the breadcrumbs of the destroyed galaxy which fell in. And from them, we can infer the story of the galaxy. So it's like, this is how we are trying to infer the story of the galaxy. Those stars, if a galaxy forms its own stars, it will form in the center of the galaxy, where the potential is very high, where there is gas, where the pressures are very high. So stars formed by the galaxy are formed in the center. But if you go further and further out in these outskirts, as you see, these stars certainly came from galaxies which fell in and were destroyed. And these are like what we call as the breadcrumbs of those destroyed galaxies. And now we are looking at them, studying them, and we try and infer the past history of a particular type of galaxy. Okay? So let's go ahead and see how we do this. The way I study this is using the Hubble Space Telescope in the past and now with James Webb Space Telescope. So we look, the field of view of the Hubble telescope is very small. So we look at a galaxy. This is another galaxy about 3.5 megaparsecs away, M81, and we put a set number of fields on the major axis and the minor axis of that galaxy. And we observe the stars in these fields. And as you can see, the galaxy kind of ends, it ends where the light stops. But actually, if you had that magical ability to look deeper and deeper, you will see that the full field is filled with stars from the galaxy, but you cannot see them. This is an image of from a ground, which we have superimposed the Hubble fields of view. But I will show you in a minute what we mean by this. So this is now a kind of a simulation. So we are kind of zooming in, and this is what Hubble does. Hubble is looking at this galaxy. It's zooming in and zooming in and zooming in and zooming in. It goes deeper and deeper in it until it can resolve the individual stars of every galaxy, of these galaxies, individual stars of these galaxies. This is done by Hubble. Now, as you know, your resolution power, your ability to resolve these stars depends on the diameter of your telescope and the distance. Okay, so you can do this for galaxies with Hubble up to a distance of 10 megaparsecs away from us. So what we call as in terms as the local volume. 10 megaparsecs is the local volume. We can resolve individual stars with Hubble and with James Webb Space Telescope. With James Telescope, we can go even further, 15 kiloparsecs, 20 kilo, because it has a larger mirror. It has a mirror of 6 meters diameter, while Hubble has about 2.5 meters in diameter. And so we can resolve these stars in the outskirts of the galaxies out to these distances, and especially in the outskirts of the galaxy. And so what is the next step? We look at those stars, we count them, and then we try and use computer models of galaxy simulations to be able to make sense of what these stars telling us. So this is a very famous simulation called the Illustrious simulation. It's rather old now, about 10 years old, or even earlier. There's a new generation which have come. There is the TNG. And these are large cosmological body simulations of a volume of 100 megaparsec cube. And they contain thousands and thousands of Milky Way mass galaxies. And using these large simulations, we can begin to develop an intuition of what those stars on the outskirts, what information it is telling us. Okay? So now I want to actually go to the particular question, which is the most interesting one, is this. Our nearest galaxy is Andromeda. That is the M31 galaxy. If we can do this exercise of finding the past history of Andromeda, we should be able to do it also for other galaxies in the past, in the little more distant away. We have the most information for Andromeda. So can we come and understand what is the accretion history of Andromeda galaxy, M31? Okay, maybe we can do it like this. Maybe it is too difficult to find every galaxy which fell in. Can we at least find let us reduce the problem to a more tractable question. Can we find the most massive galaxy which fell in? The most important one which fell in, the biggest one which fell in. Can we at least do that? Okay, so that's the question which we are trying to answer. Okay, now this is the stellar halo of the Andromeda galaxy. So the Andromeda galaxy, which you have seen many times, okay, is the thing in the center, which is in the black and white image in the center. And around it are all these stars, what we call as the stellar halo. So this is also an example of the Andromeda galaxy in the center. And around it are all those stars which are called the stellar halo. And you can definitely see by eye that there are streams around the Andromeda. And there's a big stream which is going into the galaxy. That's called the giant stream. And so just to give you a sense, this is now a similar image, but plotted in another way. This full image, that's Andromeda galaxy in the center. The other galaxy in the lower left corner, that is M33 galaxy. And if you are a stargazer or like to see, you will know the distance between M31 and M33. That is, it's almost 10 degrees across from Andromeda to M33. It is a huge thing on the sky. There is many full moons. I mean, Andromeda is one full moon. There is many full moons. The stellar halo is so big of Andromeda galaxy. The reason why it is so big is also because it is so close to us. That's why it is so big. And in physical distances, you can see, so you can see the degrees on the lower part, but on the top part, on the axis on the top, gives you a sense of the scale. So the scale of the stellar halo, it extends from 0 to almost 100 kiloparsecs. You can find stars belonging to Andromeda out to 100 kiloparsecs from the center of Andromeda galaxy. And so it is really a lot of stellar material outside the normal confines of the Andromeda galaxy. And so the question really is, how much material is out there? How much material is out there? So if you just do a simple exercise of counting how much material is out there by just counting the stars, just counting the stars that you can see, you will find that most of that material out there is about half the size of the Milky Way. Most of the material out there, outside the Andromeda galaxy, is about half the size of the Milky Way. That is a lot of material outside the Andromeda galaxy. This is a very famous survey called the PANDAS survey. It took a long time to do. It is a very, if you can see the field of view, you will see that they are made up of smaller squares. On the outskirts, you will see these small squares. Those are, each square is one field of view. So this telescope, the Canadian, French, Hawaiian telescope on Mauna Kea in the Hawaiian Islands, they painstakingly surveyed the whole area from the ground. You can also do it from the space, but you want a large field of view, and they did it from space, and it took a long time to do. So let's try and measure that material. So you can take the same diagram and you can plot the radial distribution of that material. Okay. And so I'm just doing it. So I have my units on my x-axis, that is in kiloparsecs, but I plotted it in log kiloparsecs. So you can see 1 0.0, that's about 10 kiloparsecs. Then 1.5 is about 27 kiloparsecs. And 2 would be about 100 kiloparsecs. Okay. And then you can plot the amount of material, and the amount of material also I plotted in a log axis. So it's is the amount of solar material per kiloparsec square. And so you will have a nice bump, and then there will be a slight bump on the outside, and then you can measure what is there in the green part of the halo, the green measurable stellar halo. And we can say, yes, all that material came from outside the galaxy. But certainly there must be also more material which is came from outside but settled in the center. So you can actually, using models, that means from these simulations, can actually model it. So that red dashed line, the red dashed line is like, if you measure so much material on the outside, what would be the amount of material that should extrapolate to the center? So it's like, you measure something and it is a proxy of, you see my hand and you immediately know that there will be an arm next to it. So you measure what is outside, the measurable stellar halo, and then you can automatically say, oh, all that has come has been accreted. So we use a technical term here. We say stars which are born outside the galaxy are accreted, and stars which are born within the galaxy, we call them in certain terms in situ, born within, in situ, born within the galaxy. So we can do all these measurements, and now we do these measurements for all galaxies. And we find that there is, so you will see M31 right on the very top over there. The Milky Way, this is a little older plot. The Milky Way is not down here, but has been moved. I should update this plot. But you can see that there is a course. So what I'm plotting on the left-hand side is the amount of halo material, the amount of stars in the outskirts. And what I am plotting on the right-hand axis is the metallicity. That means how metal are those rich. And you can see there is a correlation. But you can see there is a lot of material on the outskirts of the galaxy. Milky Way, the measurement of the Milky Way has now been updated a bit. It is approximately moved up to about 9. So it's no longer down there. It has moved slightly up. So about where M81 is, it has moved up over there. But there is a correlation between these two quantities, okay? And what we find is that there is a factor of 10 difference in the halos of galaxies. Some galaxies have very large stellar halos, like M31. The Milky Way has a much smaller stellar. Now, immediately, what would you conclude? You could say that the Andromeda galaxy merged with many more galaxies or bigger galaxies than the Milky Way. That's a simple, straight right conclusion. So going back to the illustration of the child eating and the breadcrumbs on the floor, you can say like this. If the child ate less, then there will be less crumbs on the floor. If the child ate a lot, there will be more crumbs on the floor, breadcrumbs on the floor. More material on the outside, more the galaxy itself has eaten. And so, this is a very nice thing. It tells you can say, what has the galaxy eaten for dinner? That's a very funny way of talking about it. What has the galaxy eaten for dinner? And so M31 has eaten a lot, and the Milky Way has eaten a bit of a less. So now many of you, this plot, I unfortunately I was in a hurry last evening. I did not update this plot, but this This measurements now have been increased. There have been many more measurements of these galaxies. And what we find is that this, if you actually, so there is M31, which is like a very single thing on the on the right hand side. And then there is a smaller M81 and on the left. And there's a bunch of galaxies in the center. Okay. So almost by eye, you can plot a kind of like a Gaussian, on the x-axis. And what you will get is that there will be a bunch of galaxies around m log halo of 9.2, 9.3, 9.2, 9.3, because they're all bunched up over there. And that particular size is the size of the Large Magellanic Cloud, which is now being eaten up by the Milky Way. So if the Milky Way was a little behind, it did not eat enough in its course of its lifetime. When it finally eats the Large Magellanic Cloud, it will jump up to the center of this plot and be in the average. So I said to you, a typical galaxy, Milky Way mass galaxy, the distance from each other is about 1 megaparsec. So that's what we said. The distance between Andromeda and ourselves is about 1 megaparsec. If I were to ask, what is the largest galaxy that a typical Milky Way mass galaxy eats? What is the largest galaxy it eats over its lifetime? The answer would be 9.3. Log 10 mass is 9.3. That is the typical galaxy that a Milky Way mass galaxy eats up is the Large Magellanic Cloud. That is a lesson you can take. Some galaxies eat bigger galaxies and some eat less, but on an average, they eat up a Large Magellanic Cloud in the course of their lifetime. That's a great thing which we have discovered about our universe. Okay, so this to give you a sense, the LMC is in the middle. M110 is a much smaller galaxy, and NGC 268 is an example of a galaxy which may be M31.8, half the size of the Milky Way. So what did your galaxy eat for dinner? The Milky Way, they eat different size galaxies, but the most typical one is the size of the LMC. And so if we look at the Andromeda galaxy, M31, which you saw, this is the image of the center of the galaxy. This is now the image, that center is put in the center, and this is all that stellar halo. We can count all that material, and we can actually find where the most metal-rich material dropped in. I will not get into the details of what these plots mean, but what we actually found was that material, which the biggest galaxy which fell in, we think left the giant stream, the number 3. It left all that material around Andromeda, which I named as the inner spheroid. And we believe, we have proposed, myself and another scientist named Eric Bell, we propose that the core of that galaxy still remains, and that core is M32, the small galaxy next to M31. It is a very particular galaxy. It's very dense. It's very dense galaxy, very high density, and it has a very large black hole at the center. And we, using sophisticated methods, can actually tell you when that galaxy fell in. And that galaxy fell in it finally crashed around 2 billion years ago with Andromeda. So we can say that the Andromeda galaxy ate a large galaxy, which was about half the size of the Milky Way. That collision finished about 2 billion years ago. And the center of that galaxy we think is M32. I want you to imagine, think of a mango fruit, right? You all have this coming from India, the example of mango fruit. This mango tree in the top of the hill, the fruit falls down, it begins to roll down the hill. Da, da, da. It gets damaged. The birds eat part of it. It falls down, and then finally, what remains, the core, which remains, is the pit, the seed. Why does it remain? Because it is the most densest part, the hardest part of the mango fruit. And similarly, we believe that the densest part, the most densest part of the galaxy is its center, and that is the M32. So all the rest has been peeled off and thrown away, and M32 has remained. I will skip this part. This we think so. In terms of sizes, so M31 is a little bigger than the Milky Way. We call that galaxy which was destroyed M32P, which would be, as you can see here, the size of it the mass of it was 10.3 in log scale. That is Milky Way is 10.7. That would be half the size of the Milky Way in log scale. And M32 would be the most central part, which would be the kern of that galaxy, the pit, the seed of that galaxy. And that would have been the third largest galaxy in the local group, which got ultimately destroyed. And we call the remnant, that galaxy, we call it as M32P, the progenitor of M32. Okay, so what exactly happens? So this is now to give you an intuition of what happens. And this is what I'm going to do, is to give you a visual history of that, okay? By giving you examples from around us. So on your right, sorry, you have M31. And where is M32? M32 is a bright dot just south of the center. Okay, look at the center of the galaxy. A bit south of that is a very bright dot. That is M32. Okay, so it is, as you can see here, M32. It's a bit south. In this part of the galaxy, it is on the north because this image has been tilted. But here, it is on the south of the galaxy. Okay, this would be how it is today. How do we imagine it was in the past? And we try and put a timeline. And this timeline is what we call the M81, M82, M51, M51B example. So first, as the M32 falls in, it has the M32P has a burst of star formation. This star formation happens in, if you know a bit of galaxies, this M81 and M82. M82 is a very large star bursting galaxy. That is the galaxy which is a bit vertical on the left-hand side. M81 is the one which is flat, and that is M82 is the vertical one, and it is having a big burst of star formation. As it is coming in, the gas with the galaxy is being compressed. Okay, stars are being formed in that galaxy, and as you fall in, it comes closer and closer. Now you can come to the example of M51A and M51B. M51A is the one which is face on, and you can see all those nice little red dots over there. And M51B is the one filled with clouds of dust. So what happens? So as you come closer, M51A is experiencing some like allergic reaction to this to the arrival of this neighbor, and the gas within the galaxy is being compressed, and that gives a burst in star formation now within the galaxy. Okay, and those red dots are the burst of star formation within the galaxy, right? And finally, the end product is after another 3 billion years, you have the end product, which is M31 and M32. So we are trying to now reconstruct uh, through simulations, calculation, but also give you an intuition of what it is, how it could presently work. So you know that the LMC and the small imaginary cloud, they are falling into our galaxy and they are eventually within 5 billion years will merge. And eventually within another 5 billion years, we will also have the merger of M31 and the Milky Way. So that's also a prediction. It will happen in the course of 5 billion years. So galaxy mergers continuously happen. And now we can do this for every galaxy out to 10 megaparsec of the Milky Way mass. And once you have the merger histories, the biggest thing which fell in, which is causing the most damage to the galaxy, then you can begin to ask the question, is the shape of the galaxy correlated with the mass, etc., etc. And that we are slowly building up that sample of doing that. And that I will leave for another talk, of what is the end product. But I'd like to leave this with you that today, uh, astronomers have become like Indiana Jones galactic astronomers.
Indiana
They
Jones.
are they are able to
Good.
reconstruct the past histories of galaxies. And we can do this, unfortunately, only for the nearest ones, uh, because the nearest ones are the ones which we can resolve with Hubble and James Webb Space Telescope. This technique works best if we can resolve the stars. We can extend the technique also if we cannot resolve the stars, but that is a bit more difficult. There are many more what we would call as systematic measurement problems, which we need to sort out. And there is a question here which says, why only Milky Way mass? And so I will say why only Milky Way mass. I will just try this last minute. I will try and explain this question. And it is really something to do with with maybe let me go to this plot. Okay, this plot over here. Okay, this is like, you can think of this plot as a cartoon. Okay, and what we can say is that this red dashed line, okay, is the amount of accreted material which fell in. Okay. Um, okay, if it is the amount of accreted material which fell in, then uh, if you go for smaller galaxies, this becomes much smaller. This accreted material becomes more small. In fact, it becomes so small that at some point you cannot distinguish what is born within the galaxy and what is coming from outside. It is like, because this thing is extruding outside the galaxy, we can measure it. And so for lower masses, it becomes extremely difficult because there is not enough material which has fallen in. And the little material which has fallen in is settled in the very center. And there is not much material on the outer part to measure, so you cannot measure it for lower mass galaxies. What about higher mass galaxies? The problem with higher mass galaxies is that there is now lots of material, so you can measure the stellar halo. But oftentimes, that stellar halo is made up of is made up of not only one big thing, but it is made up of many things. So it is there are two or three large members. So it becomes very difficult to distinguish between these two or three larger members. So at larger masses, it becomes very difficult. It becomes very difficult. At lower mass, at the Milky Way mass, and a little lower than the Milky Way mass, the stellar halo is usually built up from one large galaxy. But at larger masses, they could be built up from two or three big galaxies which could fall in, and then you cannot distinguish between these two or three galaxies fallen. This is very much connected with what we call as the stellar mass function of the galaxies. That means how many galaxies are there in the universe. And so it really depends on the mass of the galaxy. It's the easiest to do it for the mass for the Milky Way. Okay, and with this I will stop and I will take questions. I think I spoke for too long already, 45 minutes. So
that was really interesting, Father. I mean, the galaxy merger, this phenomenon is so interesting. I wish there could be some fast forward so that we could actually know what exactly happens. Thank you very much.
okay.
Now it is open for questions. If anyone has any questions, you can ask now. Just unmute yourself and ask questions. Before that, I will also invite Professor Arvind Kulkarni, sir.
Yes. Yeah. First thing I wanted to say is to thank Dr. Richard for his wonderful presentation. Sorry. And when I spoke to him, actually the person who really connected me is first Reshma Raut because she called us to Goa. Second person is Roger Farao. I contacted on his on one of the trips she conducted, and Roger gave me his number. In fact, first information about him, and then Father Richard's name came to me. When I spoke to him, he was very cordial and very accepting of my invitation. And therefore, thanks go not only to Father Richards, the primary person, but also secondarily to Roger Farao and Dr. Reshma Raut, all of Goa. So that is one of the uses of coming to conferences, number one. Second thing I want to say is that I want the youngsters and everyone to note that Dr. Richard has, Father Richard has degrees in theology, in philosophy, and in physics and astrophysics. So all 5 degrees are in 2 different areas. And in this age, it is possible to follow multiple avenues also. It is not that you are just to remain stuck in only one area of either astronomy or this, but we can you can go around different areas also. And for Father Richards, I think theology and philosophy were very close, and that is very important. I also want to say about the contribution of Jesuits to science. My first quantum mechanics lectures in St. Xavier College in Bombay were from a Jesuit father from Germany. I forgot his name now. I am 77 and memory is hurting me. But he was the first father from whom I learned the quantum mechanics. Then subsequently in other areas, that was in my MSc first year. Also, I want people to notice that people like Gregor Mendel and George Lemaitre and of course Father Sekchi, they are all Jesuit fathers. Therefore, Church is progressively contributing to active science, and I hope this situation will continue in the future also. This is a notice for other religions as well, that we need not see a contradiction between science and religion, but try to merge it as the galaxies are merging. As galaxies are merging here, religion and science can also merge. You see, ultimately galaxies are far bigger than you and me, who identify different religions and sects and divisions. So this is a lesson we need to learn from galaxies. So, with these words, I thank you very much, Father Richard, for your wonderful presence and advising us, teaching us a lot many things about galaxy merger. Thank you very much. Thank you. Bye.
Yeah, thank you, sir. So I will just read some questions which are here on the chat. The question
Okay,
is from,
sure.
the question is from Himad 3, and he's asking, what will happen to Earth when a galaxy merge with another galaxy?
Okay. I see there's also another, if galaxies are attracting each
Yes,
other,
yes,
merging, how the universe expanding.
yes.
So I'll answer both. The one must think that there is the force of expansion of the universe. So the universe is expanding, but in certain pockets, it is contracting. Okay. So one thing which the best way I can give you as a thing would be you imagine that you have a balloon, okay, which is you're blowing air through, and you see the expansion of the universe. That is the typical illustration we give about the expansion. But and then you throw droplets of water on this balloon, which is expanding. So now you know that there is a force which is attractive, and then there is a force which is repulsive. The force which is repulsive is the expansion. The force which is attractive in the case of the water droplets is water tension. It's the tension of water, surface tension of water, which makes things droplets. So when you put water on the floor, they coagulate into droplets, bigger and bigger droplets. That is because of water tension. So on the surface, you have where gravity is winning, there is a collision. Where the force of gravity is weak, and gravity goes as the square of the distance, inverse square of the distance. So if the distance is very large, gravity is weak. And in those scales, the expansion is winning. But if galaxies are close by to each other, the force of gravity is stronger than the force of the expansion, and therefore they collide. So on larger scales, galaxies expand. On smaller scales, if they are close to each other, galaxies um, attract each other, and therefore they 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 collapse. And the more the mass which you add to it, the bigger the force of gravity, so it attracts even more. So this is the reason why you will have galaxy mergers as well as expansion. Now, what will happen to a galaxy? What will happen to the Earth? Well, I think the question is what will happen to any star? So when you have two galaxies merging, in general, the distance between stars is very, very large. The distance between stars is very, very large. So let's do a simple physics calculation since we're all physics teachers over here. The distance between us and the closest star is about a light year and a half away, Omega Centauri, right? That's a large distance. You can calculate this in parsecs, okay? So let me just quickly put up those distances, which I have in the first, so that all of you have them for you. Okay, so a parsec, okay, so you have a parsec. So the nearest star is 1.3 parsecs away. Now, think of the diameter of the sun. It is very small compared to the diameter, to the distance to the nearest star, which basically means that space is empty. So when two galaxies collide, most of the stars will go through each other. They will not clash. And therefore, the Earth itself, nothing will happen to the Earth. However, this is not the full story, right? I mean, if life was so simple. There is another thing in a galaxy which is in addition to the stars, and that is gas. And gas is dissipationless. No, not A gas, you cannot push gas through each other. Gas will collide. The gas from the two galaxies will collide. And when though that gas collides, it will get compressed. And when gas gets compressed, new stars are formed. This is how we know how stars form. And when new stars are formed, often there is a range of stars being formed for different masses. There are very large stars and very small stars. And the larger stars will produce very harmful radiation. When they produce very harmful radiation, that will destroy the atmosphere of the Earth. So the Earth's atmosphere will be destroyed if there is a collision. Now let us look at the time scales. The next collision we know between the Earth and the Large Magellanic Cloud is about 5 billion years. This is also the same time that the M31 Andromeda will collide with the Earth, with the Milky Way, about 5 billion years. Even though they are very distant from each other, the reason being is again because of gravity and infall times. Larger things fall in faster, lighter things take more time to fall in. And so around that time scale, it's about 5 billion years, we already know that our sun will finish burning its fuel on the main sequence from hydrogen to helium, and they will then start having to burn helium. It will become a red giant. When it becomes a red giant, the diameter of the sun will increase as far as the radius of Mars and will envelope the Earth. So around that time frame, 5 billion years, a lot of bad things will happen to us. So we have about 5 billion years to fix humanity. But you can see it's a very long time, right? So this is what will happen finally.
Yeah. Yeah, there's long time. So that is nice. Any other questions? Students? Okay. We also have amongst us National President of Indian Association of Physics Teacher, Professor P.K. Ahluwalia. Ahluwalia, sir?
Yeah, please,
Yes.
I am here.
Yes, sir. So please say
So,
Good afternoon, sir. Good
good
evening.
afternoon, good evening. Father Richard, I really enjoyed your lecture. It was so elaborate and the pace was so good that one could understand almost everything which you said. Thank you very much. And one thing which came to my notice only today was this, when one of our members of this group shared information about Vatican Observatory. And I think that was a very revealing thing, that observatory is a very, very old observatory and is in a very good shape with people like you who are, I think, not only dedicated to theology, but to the physics also, and astrophysics and astronomy also. There was one question which was coming to my mind as I was listening to your answer to the last question. It was this, that since universe is expanding, that also implies that the gravity is diluting in the universe. Am I right to say like that? And what are the implications of that in terms of certain phenomena which we may anticipate as a result of that?
So we will not say gravity is diluting. I do not think we have enough evidence to say that the laws of physics for gravity are changing. That means if somebody does a measurement, so let's say Newton did his measurements 400 years ago of gravity and measured G, the gravitational constant. Does that gravitational constant change over time? We have no evidence of that fact. In fact, we cannot even measure that. And we assume that it is always constant. Okay? We assume that G is always constant. And from Einstein, we also understand that gravity is a deformation of space-time. Okay. But our equations, our understanding of the universe, we realize that our model of gravity does not fit the universe. That we need an extra component. We need several extra components, which we have called things as dark. We have called it dark matter as material which is which is gravitationally thing. But then we have a force which is much more stranger than dark matter, which we call as dark energy, right? And dark energy is something very strange. It is the opposite of gravity. It is the opposite of gravity. It is that material, is that force which repels everything away from each other. And we need that component. We don't understand it, but we need that component to explain our model. So rather than gravity diluting, what the physicists assume is that this dark energy is increasing over time. It's like reframing your question. And
Yeah.
it's basically ignorance, right? We don't know. It's ignorance. We have a nice fancy name for it, but it is ignorance. And there's a lot of studies now being done about trying to understand what is this ignorance? Because the way to get out of ignorance is to first to understand how much is our ignorance and measure it. And then maybe we will come up with some sort. But without measurements, we will not be able to come with, we can have some theories, but we will not be able to. But through a lot of measurements, not only the supernova measurements of the Hubble constant, which won the Nobel Prize for, in the 1990s, Adam Rees and Saul Perlmutter, and they won the Nobel Prize for discovering this dark energy. But we need much more measurements to understand what is really happening. Why is the universe expanding and accelerating? Why is it accelerating? And so we don't know. It is very, we do not know. It's a thing. So the way they talk about is not gravity diluting, but dark energy increasing. So they put it in that terms because we have no physical evidence that gravity is changing over time. That there is no G is not a function of time in any sense of the word.
Thank you, Father. There was another question which was coming to my mind, particularly in the context of Vatican, that the Galileo was in a way persecuted, and after almost 400 years, the Vatican came forward to say that that was not the right thing to do.
Correct.
So, do we now also find this thing that there are many things which we find Bible says, but they are contradictory to what we observe in the physical world?
Yeah.
So how do you really, as a theology person and then astrophysics person, balance between these two things?
So there is a lot of this is a long answer. So I'll say first one thing, that historically, by the 19th century, the church had already accepted the theory of Galileo. Already, so once we discovered the parallax of stars, once the parallax of stars was discovered by Bessel, that is the proof. That is the ultimate proof. That is many years after Galileo, right? About 200 years after Galileo. Once that was discovered, the the church never turned. Okay. What happened 400 after 400 years was another total different story about why it apologized.
Okay.
The apologies is because over time the church also got the reputation of being anti-science,
Mm-hmm.
and to remove that reputation, to say, okay, this is wrong, we apologize for something which is done 400 years ago. But
Okay.
but in all things, teachings, and of the church, people just forgot about the geocentric, and moved to the heliocentric thing. The church is not. The case of Galileo was very, and you have come to the crux of the matter. The church was not saying, okay, heliocentric or Galileo or geocentric is a problem. You don't care what is the case. But Galileo, as a person, realized that the scriptures for him, the Bible, was very important. And so he insisted that the church reinterpret the scripture. So he was
Okay.
not only doing science, he was doing theology. He was like, okay, I put on the hat of a theologian. I say you should, and they were not ready at that time to do. But since the Renaissance, since the 18th century, the church has begun to understand that you cannot interpret the full Bible as in one way. You need to understand that there are various what we call as genre. That there is poetry, there is text, there is history, and there is a theological. You can't read poetry and say, oh, this is true. So the best way I explain this is you can't take Aesop's fables you all learn in school, which is true. We know they are true, but they're not historical, right? They're not historical truth. But what is the hare and the tortoise?
Mm.
No, did it really happen? No, it did not really happen. But does it contain a truth? Yes. It contains a universal truth. And that kind of language, to be able to make this distinction. No, we're not talking about a historical truth. We were talking about a universal truth. They began to develop over time to be able to say, okay, certain parts of the scripture we understand. This is poetry. This is myth. The reason it is giving this is to give us another lesson, not to teach us about the stars and and that language has been developed in the last 200 years for the Bible. Now, there will always be uneducated people and uneducated Christians who will say, no, the Bible has always true, and every word has true, but they really do not understand the scriptures. And here the church has been insisting from the very beginning, faith, you can have your faith, but it has to go with reason. So, it goes hand in hand, and the way we explain these things now is with much more maturity. But the fact about the 400 years, it just came too late. But what is remarkable is that in the 80s, when they did apologize, it was the director of the Vatican Observatory and Pope John Paul II who really said we can do a great service by apologizing about a story which everybody forgot. But just apologize for it
Yeah.
and show that, and also as a sign that the church can say, yes, we can make mistakes. And also a sign for everybody can say, all religions have to say, we made a mistake.
Yes.
That's the kind of, which, generally nobody likes to admit that they make mistakes. Even religions, on the other hand, will never say, oh, they made a mistake, right? Yeah. That is my way of explaining this.
Okay. Thank you. I think I
Okay.
enjoyed your explanation, and that was resonating with a thought which goes in our own cultural ethos also, that there can be many interpretations of something. For example, Gita was interpreted by many people. Mahatma Gandhi ji interpreted it.
Yes.
And there are many other people who have written what you call commentaries on Gita itself, but very different
Yes.
viewpoints. Thank you, Father. I think we should have more conversations with you, both in physics
Yeah.
and on theology. And we would love to have you again here on NASNI platform. And it is a very interesting upcoming platform. And the person who shared that PDF with us is also present today, Dr. Yogesh Bhatnagar. He is very much a passionate person in astronomy and has a great collection of stamps on astronomy.
Oh.
And
Okay.
I think that is a wonderful thing to share with you. Thank you very much, Father, once again on
Thank
behalf
you.
of IAPT.
Thank you. Thank you.
Thank you.
Thank you, Mr. Advan.
Yeah. Thank you, sir. Are there any more questions?
I just have a comment.
Yes, sir. Yes, sir.
My only comment was when in 1978 an apology was sent from the Pope. I was very happy. My image of Christianity suddenly jumped up. It had a quantum jump when the apology was sent because that was long overdue. But ultimately the church did it, and I was happy for the Christianity about that. My image of Christianity has certainly gone up, though I'm not a practicing Christian, but it doesn't matter. Half the world does follow that, and that's very important. Thank you very much.
Thank you.
Yeah, thank you, sir. Yeah, so Father, that was really an insightful session we had. And this is one of the lengthy session, I must say. It is 8:29 and still we are on. Thank you very much for that. And I
Yeah,
also
I'm
would
sorry
like to
for
say,
going over time.
yeah, no. We have enjoyed it. And I must also say that NASNI is now going to the next level. We would be meeting each other through sky observation. So one of the session will be in Goa. And I would be very happy. We conduct this session when you will be in Goa. So that would be very
Hopefully,
nice
I
so that
can
we
be
meet
there.
you personally.
Yeah, I come to
Yeah.
Goa very often.
Yes.
I'm here there
Goodbye
every
in
6
Konkani.
months.
Rashma, you tell him goodbye in Konkani. I don't know that. I don't know Konkani.
So I will say that little later.
Yeah.
Okay.
Yeah.
Great.
Okay. So to formally propose vote of thanks for today's session, I will invite Ms. Tanaya Talkar, who is an MSc Part 2 Physics student. Tanaya, are you there?
Yes, ma'am.
Yeah, please.
Yes. Good evening, everyone. On behalf of National Astronomy Network of IAPT, I extend our sincere thanks to everyone who made today's talk possible. First and foremost, we express our heartfelt gratitude to Reverend Dr. Father Richard Anthony D'Souza, Director of Vatican Observatory, for delivering a truly insightful and engaging talk. Beginning with the Church's long-standing contribution to astronomy and moving through the diversity and formation of galaxies, you beautifully guided us towards the concept of galactic mergers. The clear explanations and thoughtful analogies you used, which it made those complex ideas both accessible and memorable to a student like me who is actually very new to this concept, and it was really something that I enjoyed the most. I understood from the basic, like the way you explained it. I'm really thankful. We are thankful to you. We are deeply thankful for your time as well as for sharing your expertise with the NASNI community. We sincerely thank NASNI, the organizing body of this talk, for its continued efforts in fostering a vibrant scientific community through regular interactions, which are held on the first and the third Wednesday of every month. And we are grateful to President Professor P.K. Aluwalia, sir, for his guidance and constant support, and to the Professor Arvind Kulkarni, sir, and coordinators Professor Hemant Kumar sir and Dr. Rishma Rao Desai for their dedicated efforts in organizing this session. And finally, I would like to thank all the participants for their time, patience, and attentive participations. Thank you.
Yeah. Thank you, Tanaya. And as requested by Kulkarni sir, Father, आयचो तुमचो टॉक खरेंच बरोबर आहे गुरु आणि
बरे करू.
Thank you.
Okay. Thank you. Bye bye.
Thank you
Bye
very much.
everybody.